Hello everyone and welcome to the official YouTube channel for Wayne State University's chapter of the Tau Beta Pi Engineering Honor Society. My name is Austin Heitzman. I am back yet again with another installment of our linear algebra series of tutoring videos. And today we are going to be moving on to chapter 3 section 2, which covers subspaces. So in 3.1 we covered what a vector space is. It's going to be pretty important to understanding what a subspace is, so if you have not checked out that video or you are unfamiliar with the concept, I recommend that you watch that first. But otherwise, let's dive right in, assuming that you are comfortable with that concept. So, just starting with the definition, a subspace, quote unquote, we'll call it W, of a vector space V is a non-empty subset which is itself a vector space, with respect to inherited operations of vector addition and scalar multiplication, right? So you'll remember from last time we had these funny symbols for vector addition and scalar multiplication, and that was just to indicate that there could be something else to that definition that we set, right? It's not necessarily just component-wise addition or scalar multiplication. Sometimes there's different rules written into the definitions. So basically, if W is a subspace of V, it can't change V's rules for addition and scalar multiplication. It has to abide by them. Another little component of this definition is non-empty, right? Which seems silly, but if you can always have a quote-unquote space or subspace of a vector space that just has absolutely no elements, right? That's not going to qualify as a subspace because that's trivial. It doesn't make any sense why we would even bother declaring that. So just for the sake of actually doing something, we're going to specify that it has to be non-empty. Okay. So there are a couple requirements for this, and this is going to sound very familiar if, again, you are familiar with basic vector space definitions. So of course it has to be closed under vector addition in whatever that definition is, right? Whatever the definition of the vector space's vector addition is. The subspace also needs to be closed under that same definition, and similarly closed under scalar multiplication. And these are the two big ones, but you'll remember there was also, for vector spaces, another 8 axioms, right? Abides by the other 8 axioms. Right, so basically what we're saying is a subspace has to be a space, right? Pretty basic, but the nice thing about subspaces is that there is a little bit of a shortcut to test this, because if you'll remember, all of these other 8 axioms kind of fell naturally out of vector addition and scalar multiplication. So we can automatically declare that a subset W is a subspace of V if and only if for each pair of vectors, say U and V in W, and each scalar C, the scalar does not need to be in any sort of space, it's just any real number C, we can condense all of this down into this handy formula. We can say U plus parentheses V times C. And since this should be associative and commutative, we can even rearrange this if we want. It doesn't really matter, since U and V can be anything. But this is going to be really handy, right? Because now we don't need to individually check vector addition, we don't need to individually check scalar multiplication, and we don't need to individually check all of the other 8 axioms. If this right here is true for a potential subspace, it is automatically a subspace, right? So that's going to be kind of handy. Now, there's not too much weight put on this concept quite yet, as far as I can tell in the course. It's just kind of good to understand that, you know, subspaces are a subset of vector spaces. And that being said, I do want to touch on just a little bit about intersection and union. So basically combining subspaces. Basically, so if we have like the vector space V, and we know that W1 and W2 are subspaces of V, right? Well, it might help us to understand how we can use those two subspaces to produce potentially other subspaces of V, right? So, for instance, if you have an intersection, so that's, if you remember from set theory, that'd be W1, this little upside down U thing, W2. That's going to be things common to both W1 and W2, right? So let's say W1 is 1, 3, and 5. We're not really using vectors, we're just having a set here. And W2 is 2, 3, and 6. We'll also throw a 5 in there too for a later example. Well, in that case, then W1 intersection W2 is only going to be the things common to both, right? So in this case, it would be 3 and 5. But we're not going to include anything like the 1, 2, or 6 because that is exclusively part of one of them, right? So the handy thing to know about this is that the output of this, so the result of W1 and W2, let's say that this equals W3. W3 is inherently a subspace of V. We don't need to check anything else. If we are certain that W1 and W2 are subspaces, we take the intersection of those two things, the result is a subspace, right? However, say we have a union, right? So if you'll remember, the union is going to be this right side up U sort of symbol. That represents things which are in either W1 or W2 with no duplicates, right? So if we're using our other example here, I could say that W1 union W2, well, I'm just going to go straight through. I have 1, 3, 5, and then from the other list we have 2. We have 3, but I already have a 2 in this. Sorry, I already have a 3 here, so I'm not going to add that again, but I don't have a 6 yet, so I'll add a 6. Similarly, there's already a 5 in this list, so we don't add it again. We just close the space. This, the result of this, let's say W1 union W2 is W4. Well, W4 is not necessarily a subspace of V. It could be. We need to check. So that might just be a good thing to keep in mind. However, based on this section and based on the work that I've done kind of looking ahead and continuing on this course, the really important thing from this section is actually going to be span, right? We're getting into the big guns now. So, in order to define span, we need to remember linear combinations, right? So if you are a little rusty on that, I recommend going back and checking out our previous videos or just doing some brushing up on your own. I've said it before and I'll say it again, this course builds on itself, right? So if there is a section that you're not super comfortable with and you kind of let it slide, you're going to be in big trouble as the course goes on because you're not going to be able to follow things as well as you should be. That said, let us look at span. So a span of a set we'll call it S. And it'll be just a set of vectors right now, but it could also be like matrices or polynomials, etc. Set of vectors in space V is denoted like this, like span parentheses S. And basically, the span can be defined as the set of all possible linear combinations of vectors in S, right? So this should look really familiar to you. If you remember when we covered linear combinations, this is pretty much exactly the type of notation that we used, right? And going back to what we were just talking about subspaces, it can be taken as a true known fact that if S is a set of vectors in vector space V, then span of S is inherently a subspace. And this is true. We're not going to go through the whole proof, but essentially you can anchor yourself in the idea that a span of any set is a subspace because every subspace can be written as the span of some set, right? The span is essentially a description of the subspace. And that's true because, I mean, what the span literally does, right, is it is essentially a list of all the vectors in the subspace, right? Because if you remember from like linear combinations, what we're doing is we're giving kind of the blueprint of how these vectors can be combined, right? So geometrically, like if you feel like you need to like anchor yourself in some sort of picture, which is always a good idea. Basically the span, just like linear combinations, right, is like every point we can reach on this graph using this set of linear combination, right? It's essentially like, where can I get to on this graph using the rules laid out to me by the subspace, right? So this is going to be a super important concept when we start covering like basis and change of bases, which is pretty much the heart of linear algebra. So highly recommend you actually like going through, doing a lot of problems. We will be covering an example of finding span in this video, but practice makes perfect. So definitely make sure that you feel super comfortable with this. Before we do our example though, I do want to just touch on a concept of like null and column spaces, right? So starting with a null space, the null space of A is going to be denoted this n parentheses A is the set of all vectors in R superscript n such that A times X equals 0, right? And you'll remember that this formula is a description of a homogeneous system. So now we have a space that will describe homogeneous systems. And this is inherently a subspace, right? And we can prove this pretty easily because if you have A, and remember we have this U plus V times C, we can write it U plus CV, and you can expand this by the distributive property. Well, if C equals 0, then we have AU plus CAV. Well, U is going to be 0, right? Because the whole space is just 0 vectors. And then we have 0 times A, also times 0, equals 0. So that means that anything we put into this, its output is always going to be within the vector space. And of course 0 is in the vector space, that's all the vector space is. So the null space is a vector space, it is also a subspace. Right? Similarly, we have column space. Column space of A we can denote that as like COL parentheses A. That is going to be the set of all linear combinations of the column vectors of A, right? So if we have A equals this 1, 0, 0, we'll just do the identity matrix. The column vectors are going to be basically the vectors that make up the individual columns of A. Right? And the kind of test here, so kind of like we had AX equals 0 for null space, well, hopefully this will ring a bell, but this is going to depend on AX equals B, right? And we can affirm here that the system AX equals B is only consistent if B is in A's column space. I am going to write that using the notation because I'm running out of room. Right? So now what's happening here is we've already learned these little caveats, right? We've already learned about AX equals B when we learned about multiplication, right? Vector multiplication and matrix multiplication. We've already learned about homogeneous systems. And now we're learning about vector spaces and subspaces. And basically this is the book saying, hey, this thing that you learned like 2-3 weeks ago, that's still relevant. We can use these new things to describe things that we've already learned, right? So yet again, super, super important for you to be solid in every single one of these chapters. Okay, so without further ado, let us look at our example. This example is going to relate to span as well as linear independence. And, excuse me, so basically if a set, when we put that into a matrix, an augmented matrix, if there is a pivot in each column, then this set is going to be linearly independent, right? Same old thing we have been doing this whole time. We're just applying it in different ways now, right? So, as you can probably tell, based on that, we are going to be doing some row reduction. So to set up this problem, I see these two vectors. We are basically being told that there's a set that can be described within these two vectors. So now what we need to do is put those two vectors into an augmented matrix, right? So I'm going to write them as the two columns and draw this line. If you remember, we did this in like chapter 1. And I'm going to augment this with a variable matrix, just so we can see like how things are going to go about being manipulated, right? Now from here, all I need to do is reduce it. I think pretty much every video that we have done so far has dealt with row reduction. If you don't know this by now, please go back and study it. Seriously, I cannot stress like that. This is like the tool we use in order to do pretty much anything in this course. For that reason, I'm not going to cover it very heavily right now. I'm just going to go through the process and do it. We'll do 2 R1 plus R2. Gonna take us to R2, and then I could just add rows 1 and 3. Oh. And remember, whatever we do to the left side, we need to do to the right side as well. Nope. Just be sure if you sit through it, you do it carefully, like I clearly did not just do there. All right, and this is a pretty simple problem. We're already almost done with the reduction. And for this last one, just so we can see what I've done, I'm going to write it not in a very reduced form yet, but off to the side. It's going to be important to really understand what we're working with. If we get common denominators, actually folks, I just caught a mistake. I am not going to edit it out because it's important to see that mistakes happen if you code too quickly. Again, basically what I did here is this should be a -2. That was wrong. So from here, let's see, this is still valid, but this should be -2 up +2. Yes. So 2 times row 2 plus row 3. So instead of this, we have C plus B plus 2 times all of this junk. Alright, sorry about that, but again, don't make my mistakes. Go through this slowly and really know what you're doing. So once again, we need to simplify this. -2b over 3. We get common denominators here. Yeah, this is looking much better. So this can reduce, we have 2a minus b plus 3c over 3, right? And if you remember, so for this to be consistent, right, we don't want to have like an instance of like no solution. So in that case, this needs to equal 0, because if it didn't equal 0, then you would have 0 is equal to some number, and that does not make any sense. So when we're asked to find the span, remember the span is kind of the description of the subspace. So we're going to need to put this caveat into our description of the span. And we can do that, again, if you'll remember, we want to describe this in as few variables as possible, right? So if we have like a free variable that will depend on the other two, then we want to be able to write it like that. In this case, well, this can also, since we have 3c over 3, right? Let's see, we can easily pull that 3 to the, that c to the other side. We don't want it to be negative though, so we can say that c is equal to b minus 2a over 3. So now we know that this needs to equal 0, and we are pretty much ready to write our span. So the span of S, in this case, again, a span is going to be a description, so we're just going to write like the blueprint of what a vector in S must be in order to be within this space. So there's going to be A and B. The first two, they don't matter, they're A and they're B. But the third one, again, needs to have a very specific form for this to work. So this is going to be b minus 2a over 3, such that we have two conditions here, right? We have a and b are real numbers, and I'm going to need to write this a little down here because I'm impeding my space. B minus 2a over 3 is equal to 0, right? So we have two parts of this question though, right? So we found the span of S. We have not yet determined whether S is independent. It's a pretty easy task though. We do have this row of zeros. However, that's essentially saying that there's more than is strictly needed to describe this system. We do, however, have a pivot in each column, right? We have two columns and we have two pivots. So S is independent. It is linearly independent. So now we have described our span. We have declared that S is linearly independent, and so we are done. So that was kind of a lot of information. I recognize this. I tried to do it in a sort of linear fashion, where it all built up of each other. However, thank you for your patience as I tried to figure out how to do that. Like I said, span is going to come up very often in the rest of this chapter. We're going to absolutely need it for ideas of like basis. I took for granted that I knew what I was doing, and then I took the exam and then I realized I did not, right? So do not make my mistakes. Really actually go through this even if the exercises seem redundant. Highly recommend that you do what you can to really wrap your brain around this, because your future self will thank you. If you need some help brushing up on past concepts, if you're feeling like you're kind of not understanding like more of the rudimentary stuff of this, please feel free to go back and check out our previous videos. We have all of this covered sections up to date, from chapters 1 and 2, as well as, of course, the start of chapter 3. We also, on our channel, have plenty of other STEM tutorial videos for other classes you may potentially be taking, whether it's math or chemistry, electrical and computer engineering, mechanical engineering, anything you need. We probably have something for it. So feel free to like and subscribe for new videos coming out. Study hard. I'm wishing you luck, and I will see you next time when we cover section 3.3. Bye, folks.